All right. Now, we'll do a little bit of quick history here. You remember Kirchhoff? Okay. Kirchhoff, like many scientists back long ago, they were involved in lots of different things at the same time. All right? Gustav Kirchhoff was involved with Kirchhoff's rules and all that sort of thing, but he was also involved in radiation. Okay? He studied some radiation, and he was looking at what objects looked like at different temperatures. Now, some of you may have noticed this already. I don't know. If you have a range top at your house or apartment, a range top. You know what a range is? Okay.
Beginning of the year, people.
The coil?
Stove.
The stove. A stove, this thing you call a stove, you youngsters.
I call it an oven.
All right. No, the oven is where you put things inside. So you set things on top. Okay. Everybody knows what a stove looks like.
Yes.
Okay. When it's off, it looks like this. When it's on, it looks like this. Sort of.
The stove?
Yes. All right. Now, Kirchhoff noticed that when things were certain temperatures, solids at least, and liquids, not gases. Gases are a little different. When solids and liquids were at a certain temperature, they were always the same color no matter what the object was. Okay? So like a kiln. You know what a kiln is?
Yeah, with their fire clay thing.
Yeah, it's like a very hot oven that they cook pottery and things in like that. And back then they would blow glass to make vases and
a boss.
They still do?
yeah, they still do. But most of that's made industrially now. Back then, someone would literally blow the glass, like for test tubes and things like that. So, a lot of these scientists had to make their own equipment because there wasn't a place that you could order it. Okay? And so he noticed that when he put glass or different things in the kiln, no matter what the object was, once it reached the same temperature as the kiln, it was the same color as everything else inside. Okay? And this started off a whole study on what they call black body radiation. It's kind of a long story why they call it that. But what they discovered was that if you had what they call a black body, it was like this kiln. Okay? If the kiln was not radiating heat, and you looked inside of it, because there was an opening where you put stuff inside, right? It would look black inside. Okay? If no light was coming out and light was only going in. Because what was happening is the light's going in, it's reflecting around, and as it reflects around, it gets dimmer and dimmer and dimmer. So like if you take a shoebox, even if the shoebox, the inside of the shoebox is totally white, and you punch a hole in the side of the shoebox, and then you hold that shoebox up to your eye and you look inside the box, it looks black, right? It's called a black body because no radiation's coming out of it, all right? Well, he noticed that this black body, if you would heat things up inside, the colors that would come out the hole would all be the same, as long as they were the same temperature, all right? And they got this temperature range, like at a certain temperature it's a certain color, and a certain temperature it's a certain color, okay? Now, they use this to give you the temperature of stars right now. So like a red star is a cold star, okay? And an orange star is warmer.
What's a cold star?
Cold, relatively speaking. That's a good question. Okay, when they say cold, like our sun, the surface temperature of our sun is, oh shoot, I don't remember. It's like 6,000 degrees or something like that. Golly, don't quote me on that because I don't remember.
It's on video.
Yeah, I know. It's on video, so I said it wrong. But like you're talking, you know, maybe 4,000 degrees or 3,000 degrees. All right? So the hotter the object gets, the more it glows towards white. And once it gets past that color, even hotter still, it gets bluish. So some stars, which are really hot, are a bluish color. Okay?
Is that why the star is blue?
What? Yes, some stars are blue. Okay, so at any rate, why these things are certain colors, okay, why these things are certain colors, Kirchhoff wanted to know and he couldn't figure it out. So he offered a challenge, okay, back in 1859, and the challenge had a prize with it. He said, anybody can figure this out, I'm going to pay you, I don't remember what it was. It was a large sum of money for back then.
Oh, I thought you were telling us right now. I was like, okay.
No, not you. It's already figured out. Okay? So that's 1859. All right, in the year 1900, okay, a person by the name of Max, should I spell it right? Max Planck. Planck or Planck. All right, Max Planck, the reluctant father of quantum physics. Okay? He comes up with an equation that describes this black body radiation and why it's occurring the way it is. Okay? In his explanation, he comes up with something, when he's working it out, that gives this. That the energy of an electromagnetic wave is equal to HF. Okay? Now, H is now referred to as Planck's constant. At the time, it was just a constant. They didn't name it after him yet, because he didn't name it after himself. Okay? H is a constant. F is frequency. Okay? Now, in this, he said, look, it came out of the equations that the energy of an electromagnetic wave, the frequency determined the energy of the wave. Not only did the frequency determine the energy of the wave, but that they came only in these small components. Okay? So the waves came in a unit of energy, which is really weird. Because normal waves, the amplitude determines the energy of the wave, not the frequency. And the wave is kind of continuous, right? So there's not a discrete amount of energy for a wave, right? Because the wave continues. So when he came up with this, his equation worked to figure out why black body radiation was the way it was, but he never really kind of believed this part of it. He thought it was some sort of mathematical anomaly, some fluke of the physics that was not really real. Okay? And so he took the prize. But this, he's like, it's weird. So he just kind of leaves it. Okay? And it just sits on the shelf. Or in a paper. Okay?
On the shelf.
F equals frequency. H is a constant. Energy, of course, is in joules, has units of joules. All right? Now, the constant turns out to be this. And so, actually, get out your equation sheet. I want you to find the constant. Because you'll be using your equation sheet extensively in modern physics. All right? No, I'm sorry, not your equation sheet, your constant sheet. Sorry. Get out your constant sheet, because you need to find all of these values. All right? You're going to get two of them. 6.63 e to the negative 34th. Oops, 34th. Joule seconds, or 4.14 e to the negative 15th eV seconds. Okay, there's going to be a couple other ones that are going to pop up along with that one. Let's just start. Actually, you know what? I'm going to write them up on the board over here because we're going to end up using them a bunch.
Oh, it fell.
Don't write down what I did.
Back fell.
What did you write down? I don't write down.
Okay, there should be another one with Planck's constant in it.
HC.
HC. Oh, very good.
There you go.
Okay, give me the HCs.
1.99. E to the negative 25th.
Negative 25th.
Joules per meter.
Joule meters or joule per meter?
Joule meter.
Joule meter. Okay, and then there's another one.
1.24 e to the 3.
Come on, pal. This is
Electron
ridiculous.
volts nanometers.
EV nanometers?
Yeah.
Okay, EV nanometers. Okay?
Is that Planck's quantum?
Which one do we really need?
All of them.
No, don't tell me that.
Now I'm going to rewrite this one right here. This one's the same as 1240 EV nanometers, okay? That's the same one. All right, we have 4 different versions of Planck's constant. One is Planck's constant by itself. The most basic one that looks probably the most familiar to you, or the one where the units at least look most familiar, is this one right here, joule seconds. This one is in standard units. Okay? This one, EV seconds. Now I believe we've talked about electron volts already a while back. Maybe, did we? Real briefly, okay? Here's how this works. What the heck is an EV? All right? If I have 2 capacitor plates like this, okay, and I have this thing charged up to 100 volts, and this would be my plus side and minus side of my battery. So this is the plus side of my capacitor, and this is the minus side of my capacitor. Now, if I take an electron, and I put my electron right here, my electron's right there next to the negative plate, and if I crank up the volts to really big, 100's not big enough, but if you crank up the volts really big, electrons will start to shoot from one side to the other. Okay? Because they'll spark across. Alright? Now, over here, they have energy. And over here, as they fly across, they have energy. What kind of energy do they start with? Electric potential. And what does it turn into? Kinetic. Alright, so we have conservation of energy. Energy where it begins equals energy where it ends. On the other side, we start with electric potential, we end with kinetic. The electric potential we start with is V times Q. Remember, I can't use K, QQ over R squared because I don't have a radial geometry, right? So I have to use V times Q. And this is 1/2 mV squared over here. Now, the volts are 100 volts. The charge is charge of an electron. Now that's 1.6 e to the negative 19 coulombs. Is that right? You have your constant sheets out?
Yeah.
Okay, now that's another thing. You're going to have to, if you don't remember these numbers, you're going to have to look them all up. And they're all on your constant sheet, right? Okay, what would I put over here? 1/2 mass of an electron, which is 9.11 e to the negative 31st, right?
Yeah.
Kilograms v squared. And I can find v, the velocity, that it will strike the other plate. Now, just as a side note, what if I start halfway in the middle with my electron? What changes in my equation? Well, the distance doesn't show up, but the voltage does, right? So, what voltage will I be at if I'm in the middle?
50.
Okay, I'm going from 100 to 0, or in the middle it'd be 50 to 0, right? Because it changes linearly. Very good. All right, now, this is my energy in joules. So my energy in joules is going to be 1.6 e to the negative, what, 17 joules. Negative 17 because this just moves it 2 places, right? Okay, now that's a ridiculously small amount of energy. So what they do sometimes is they try to make the numbers a little easier to read. Now, this is very unphysics-like, okay? Because in physics, they generally keep one set of units, right? And they did this forever. But when they got down to the size of an atom, they found out that some of the units we were using were like really, really ridiculous. Not just marginally ridiculous, very ridiculous. So they picked up on what the chemistry people always do, which is make a new unit that's appropriate, right? So, here's what they did. They made up a new unit. It's called an electron. back up. The charge of an electron. How many volts do I have here? VQ, 100 volts. What's the charge of an electron? 1 electron. And what do you get? 100 EVs, electron volts. So an electron volt is a unit that's made up, just like in chemistry, instead of saying how many atoms you have, you use number of moles, right? Because number of moles is a little easier. Okay, right here, instead of saying the charge is 1.6 e to the negative 19th coulombs, we say it's an electron charge. Does that make sense? So what we do is we place in how much electron charge it has instead of how much coulomb charge it has. Okay, because a coulomb's a really big unit. And when you get down to electrons, atom size, it's a ridiculous unit. Now, that's the beauty of it. So how much energy do I start with? 100 electron volts. Ta-da! Very easy. However, what if I was to leave this down here then? In units of electron volts. So over here I'm going to have 100 EVs.
You have nasty velocity.
Yes. Can I solve it this way? Technically, yes. But will my velocity come out in meters per second now? No. I'm going to end up with EVs divided by kilograms square root. That's my new velocity measure, which is kind of an odd unit of velocity, right? Now, does that mean you cannot do that on the exam? Well, no. If you want to, you can really do this on the exam, but you better put the right units down. So what most students will do is if I have 100 EVs and they say, well, what's the velocity of a 100 EV electron? You'll go, oh, well, I'm going to end up with really crappy units. So how do I get around that?
Convert it to joules.
I convert it to joules. How do you convert 100 EVs to joules? Yeah, you multiply by, what is an E? An E is 1.6 e to the negative 19th coulombs. So all you do is multiply, replace that by what an electron is, right? So if I gave you that you had a 25,000 EV amount of energy, you could convert that to joules, which you can by just multiplying by 1.6 e to the negative 19th joules per EV, or by multiplying that in for the E, right? And then that gives you your answer in joules, okay? So when you see EVs, it's just a different unit for energy than joules. All right? Now, so the question is when will you use this one? Well, whenever you have EVs in your problem. Okay? When will you use this one? Whenever you have standard units with joules. Okay? So you just pick whichever one's appropriate. And you've all had chemistry, and you know how to do that already. Because you use whichever, like when you're doing PV equals nRT, if you're using milliliters for volume and torr for pressure or whatever, then you got to use the right universal gas constant, right? The one with the correct units on it. Yeah. Okay. Now, what the heck are these? Okay. All it is Planck's constant multiplied by the speed of light. So if you take this and multiply by the speed of light, you get this one. Okay. Now look. Joules times seconds times the speed of light, which is in meters per second. That's how you get joule meters right here. So all this is Planck's constant times the speed of light in standard units. That's Planck constant times the speed of light in EV units. All right? Now, this HC comes in handy lots of times. So we have 4 different constants, all related to Planck's constant. Okay? Now, once again, Planck did not really believe what he had discovered. All right? And for about 5 years, nobody really cared that he had discovered that electromagnetic waves are frequency dependent for their energy, which is really, really, really weird. It's not like any mechanical wave we know of. It's a new beast. along comes, well, first of all, here's what they're discovering. Around the turn of the century, they had discovered, we talked about this last time, light comes down and electrons pop off with a velocity. All right? Now, everybody, this is called the photoelectric effect.
Nope.
Okay, now, the photoelectric effect. Classical physics describes this. A wave comes in. The wave transmits its energy to the metal, knocking electrons from the atom. Now, they didn't really know what an atom was yet, but they knew that the atom now could be parted somehow or another, separated into charges. Okay, now they say, okay, let's study this. If I send in a brighter light, okay, because this is dim and this is bright. Okay, according to classical physics, brighter light would mean what?
Higher amplitude.
Higher amplitude, bigger wave. So you send in a bigger wave. The bigger wave comes in. And according to classical physics, a couple things could occur. One thing that could occur would be more electrons. Okay, because we have more energy coming in, and this would be more kinetic energy going out, right? That would account for it, right?
Yeah.
Energy in equals energy out. Another alternative would be this, is that if you send in a bigger wave, then a single one could pop off, but how can I get more kinetic energy out of a single? It'd have to go faster, right? So more kinetic energy would mean higher velocity. Okay? All right. So, but here's what they discovered. What they discovered was this. You take this yellow light, you shine this yellow light on, it's dim. And out pops a yellow electron. Well, an electron because of the yellow, right? And it has kinetic energy. Ta-da! All right? Now, they want to measure how much energy this yellow electron has. Here's how they do it. They've got a little evacuated tube. They have two plates inside, so they've made a capacitor with a vacuum in between. All right? They have a variable voltage battery. Or what they would do is they would have a resistor in here to give you a different amount of voltage across here. I'll just do variable voltage because it's easier. Okay? So you have a changing EMF, which changes your voltage difference. Okay, which one is the negative plate?
One on the left. I'm right.
Okay, so this is your negative plate, this is your positive plate, right? Okay, now what they're going to do is they're going to shine light this way. Okay? The light shines on here, takes an electron, pops it off. The electron pops off with a certain kinetic energy. Okay? How do they measure how much kinetic energy it has?
Velocity.
Yes, it's really slick. What they do is when they dial this voltage up, this side becomes positive, that side becomes negative. What does this electron want to do?
Resist the movement.
Well, it's going that way, but
Negative.
it wants to go that way. So what they do is they dial it up, dial it up, dial it up, and they have a little ammeter here. Guess what? When they dial it up, what happens to the current of these electrons going around here? It goes down, and it goes down, and it goes down until they dial it all the way, and then they get the magical spot where the electrons don't make it anymore. And so what happens is these little electrons, the most energetic ones, the ones with the maximum kinetic energy, they go all the way out and they just don't quite make it. And they stop. Okay, when they stop, what kind of energy do they have now? Electric potential. So all of their kinetic has been converted into electric potential, right? And how much electric potential is that?
All the kinetic.
Equal to max kinetic energy.
It's V times Q. What's the V between the plates?
Whatever you put in.
Whatever you dial it up to. Ooh, but what's the Q between the plates?
One electron.
An electron. So if you dial this thing up to, say, 47 volts, and they stop, then how much energy did they have?
47 EV.
47 EVs. So the energy would be 47 EVs. Or you could convert it to joules if you wanted to, right?
Multiplying by that constant thing.
All right. This is called a photoelectric circuit. The photoelectric circuit is where they shine the light on here, they pop them off, but they use a back voltage, what is also called a stopping voltage, to stop them. And once they can stop them, they know exactly how much energy they had. Now this is really crazy. They can find the kinetic energy of moving electrons, which they can't see. Pretty slick, actually. It's really quite slick.
Like a kangaroo. Word.
I'm not sure I get the connection there, but I'll just shake my head and continue.
Just go with it.
I'm going to go with it. All right, now, so when they do this, here's what they get. Here's what they get. When they shine this yellow light on here, they get a certain maximum kinetic energy. And then they go, okay, so let's jack up the brightness. And when they increase the brightness to very bright, electrons pop off. And sure enough, they get more electrons. Just like they expected. But guess what they got when they dialed up the voltage? They all had exactly the same maximum kinetic energy. Now, whoa, that doesn't seem right. So they make it even brighter. And they still get more electrons like they expect, but all of them have exactly the same maximum kinetic energy. They say, well, let's go the other way. Let's make it really, really dim. They make it really, really dim. And sure enough, they get less electrons popping off, just like they expect. However, guess what the maximum kinetic energy is? Exactly the same. They're like, that doesn't make any sense whatsoever. Okay? So then they say, okay, well, let's try a different color. So they do this. And they try it with green. They try dim green. They try bright green. Guess what? They all get the same max kinetic energy. Oh, but wait a minute. All the greens are the same max kinetic energy, but how does the green max kinetic energy compare to the yellow max kinetic energy?
It's less.
It's more.
It's more of those others.
Man. So they tried blue. They tried blue. Guess what? Blue has the maximum kinetic energy. How does blue compare to green? More. How does it compare to yellow?
More.
Even more. So, yellow has the maximum kinetic energy, green has the maximum kinetic energy, blue has the maximum kinetic energy, violet has the maximum kinetic energy, which is greater still, ultraviolet is even greater, and then the real kicker. Guess what? They tried red. And they get nothing.
Nada.
Because it's so low.
They try really, really bright red, bright enough to roast your skin. They get nothing. Now that makes no sense, because according to classical physics, we should be able to just continue to shine the bright red on there, and eventually the electrons will pop free. All right, into this wild conundrum. Conundrum, it's a college word.
Three syllables.
Why are you using the
Conundrum. Well, I can't spell it, but I can say it. All right, into this conundrum steps a young man who has been working at the patent office, and this is 1905, and Einstein publishes in 2005 5 papers. Okay? That's in 2005. 1905. Yeah, he just did it a couple days ago. That's right. It's really famous. In 1905, he publishes 5 papers, and one of the 5 papers is about this. This is the only one Einstein ever wins a Nobel Prize for. He explains why this occurs. Okay? And Einstein at the time was an unknown
Kid.
Yeah, he was a young person. I don't remember, he was 20s or 30s, but he was young for a scientist at the time. And he wasn't working at a university or anything. He did most of this stuff on his own. And he explains this, and he resurrects Planck's idea. He said Planck was absolutely right. He says, look, this explains everything. Why does red produce nothing? Or what? First off, why does yellow produce a certain frequency only? A certain energy only? Because yellow is a certain frequency and only has certain energy. So why does green have more energy than yellow? Because it has a higher frequency. Why does blue have more energy than yellow and green? Because it has a higher frequency. And he even explained why red produced nothing. Okay?
There's no frequency. What?
Red has a frequency, but what he said is look, what you have is this material. Okay, here, let's go back to chemistry. All right?
I love chemistry.
You have your nucleus. You've got your electrons out here, right?
Ooh, what are you saying about physics?
You have your electron out here. You remember how you ionize a gas? It takes a certain amount of energy to break the electron free, right?
Yeah.
Okay, Einstein says, look, in a solid, we have the same thing. There's a certain amount of energy required to break the electron free from the metal. They don't just float away by themselves, right? And so you have what's called an energy well. So the electron is down here in the well. And the well has different steps. Okay? Some electrons are here, some are here, some are here, some are here. The ones that are deeper down in the well are the ones closer into the nucleus. Does that make sense?
Yeah.
So if they're way down deep, it takes a tremendous amount of energy to break them free. Okay? The ones on the outside are the easiest one to break free, but it takes a minimum amount of energy to break them free. This amount of delta energy is required to break them free. Guess what? For the particular metal that they are working with, red doesn't have enough energy. Red hits this electron, it jumps up but not high enough, and it falls back in. Oh.
It's like
Now,
a bird, John Fly.
here's the other thing he said, is that light is different than what we expect. Light comes in these little packages of energy. How is it possible for a frequency of light to have only a certain amount of energy when a wave is supposed to be forever continuous, right? He said, well, they're not.
They come in packets of
They
waves.
come in little packages of waves. And he called them, he invented a name, he invented the name of photon.
So they're not really waves anymore. We can't call them waves. Just call them...
Oh, yeah, so here's the really crazy thing. You know, what, 50, 100 years earlier, they had solved the problem that they'd been fighting about for 200 years. What is light? And the double-slit experiment shows that light has to be a wave. But the photoelectric effect shows that light has to be a particle, a
Oh my gosh.
clump.
Oh my gosh.
Again!
And so Einstein says, well, they're both right. We've just been thinking about it wrong. If the evidence says it's a wave, it must be a wave. But this evidence says it must be a particle. So it's a particle. So it's a wavicle or a photon.
Oh, wait.
I just made that up. It's a photon. I just made it up.
I'll put that on my ATO.
Actually, photon comes from a Greek or Latin word, which I don't remember. Look it up. It means...
Have you ever had
all right, everybody. So a photon is a little package of wave. A wave packet. Okay? It's the beginning of what we call wave-particle duality, where everything is really a wave and a particle. Okay? So why don't we think of, what, this physics book? Why is this physics book not display any wave properties? Ooh, we'll discover that in a little bit.
Because it's a
It's a
solid.
wave. All right. It does have wave properties. The problem is that the bigger the object gets, the harder and harder it is to see its wave properties. Okay? And when you get into statistics, we are made up of lots and lots of atoms. When you put all the atoms together, the wave properties of all of them merge into a single glob, essentially, which we call a particle. You don't see the particle. So you don't see the wave properties until you get down small. So why did we never see this wave-particle duality? Because we hadn't gotten down to about the size of the atom yet. The atom is where you start to see these wave properties in what we would normally consider objects. And the smaller you get, the more it behaves like a wave. Until you get massless. And when you get massless, then you display the maximum amount of wave properties. Okay? So light is massless. So light displays the maximum amount of wave properties. All right? But it still has particle properties. So, here's what Einstein said. Photons interact with electrons on a one-to-one basis. Okay? All right? What happens is here's your electron waiting for energy. You send in a violet photon. The violet photon hits the electron. The violet photon ceases to exist. It disappears. And when it disappears, it gives its HF energy to the electron. Now the electron is buried in this well of different steps. And it's at the top spot, so it only takes this certain amount of energy to break it free. Okay? So all of this energy is transmitted to the electron, but some of it, which they call the work function, which is like ionization energy, some of it must be taken away before it can exit, right? So let's say that this ends up being, I don't know, Violet, let's make up a number. Say this is 3 EVs of energy. Let's say the work function is 1 EV. Then how much energy is left over for this thing to fly away and be free? 14. 2 EVs. So the kinetic energy that's left over, the maximum it can possibly have, would be 2 EVs, correct? So here's his equation. The kinetic energy max that you'll get will be equal to the energy of the photon minus the work function equation.
We can use that with that symbol thing you.
Yeah, which is this. Kinetic energy max equals HF minus the work function. There you go. This is the max kinetic energy of the ejected electron. Okay? And this is the photon energy. So really the equation is remarkably simple. It's just an energy equation. You start with a certain amount of energy. You need a minimum amount to break it free. Whatever you have left, it flies away with kinetic energy. That's it. Energy before equals energy after. That's it. Piece of cake, really. So why won't red work?
It doesn't have any.
Yeah, the red comes in and its HF is energy is less than 1. 0.8 or something.
0.99999.
Yeah. If you have 0.9999 energy from the photon, it won't work. So below a certain frequency, you get nothing, no matter how bright it is. Because it's not, you know how you put change into, well, most of you don't know this anymore because you don't use change anymore. Like an old-time vending machine, we have to plunk quarters in.
Yeah.
Okay, the vending machine won't take like pennies. Pennies are too small, so they're useless, right? Okay? But like in a vending machine, if you needed $1, you could put in 4 quarters and it would work. But this won't work like that. You've got to hit it with enough because they interact one at a time. So you can't hit it with a red, get it halfway up, and then hit it with another red and knock it free. You hit it with a red, it's not enough. You hit it with another red, it's still not enough. You hit it with another red, it's still not enough.
So
So that one has to be.
So the 1 has to be enough to knock it free. They interact on a 1-to-1 basis. You can't take 2 reds, add them together, and hit it.
So you need a
One
dollar.
red, move it up a step, and then hit another red.
I need
Well,
a dollar.
if this step is less than what red is, you could take it from this step to this step. Sure. But it wouldn't be enough to ever get it free because you need at least 1 to get it from this step out.
So like the brighter it is, the more electrons they escape because it's more energy because they have several photons.
Yes, and so Einstein's new view of brightness, when we turn the lights up to be brighter, that doesn't no longer mean that the wave is bigger. What does it mean?
More photons.
It means more and more photons, more little packages of waves. So when we turn the light on brighter, more of the little packets are coming at you.
It's like kicking an anthill harder.
Oh my God, I'm getting it
All
All right,
Sticking it some anthill.
so that's the photoelectric effect.
Freaking out.
Amazing, quite frankly. Now, okay, everybody? In case they ever ask us on the test, which experiment proves that light is away? Double slit experiment. Which one proves that light has to be a particle? The photoelectric effect. Okay?
Wait, let me read.
This right here. This whole thing we've been talking about is all the photoelectric effect.
What was the
Okay.
one for, what's the name? The light for wave? Right. Double slit.
Double slit, it's actually Young's double slit experiment. And the photoelectric effect proves that light has to be a particle. And Einstein put it together and said, well, we got a new thing called a photon. Wave-particle duality was born. Okay?
This sounds complicated.
It does sound complicated. And the math gets kind of wacky.
Yeah, it is.
But not in this class. The math doesn't get really bad in this class. In fact, even next year in Physics C, well, we won't even address this in Physics C. Everybody, here's our equation. It's K max equals HF minus work function. All right? This is important, so watch this. Y equals mx plus b. Oh no. Y-axis, x-axis, slope, and intercept. Okay? Hey, by the way, well, hang on, we'll do this in a second. All right, so what's my graph going to look like? A line. What kind of line? A line like this. Okay? But only like this.
Not like that.
Okay?
That's imaginary.
You see this down here?
Does not exist.
That's imaginary. Thing.
This does not exist down here.
Can't have negative energy.
Oops, wrong one. You can't have negative energy, negative kinetic energy. You can't be less than moving, right? So, I'm sorry, less than not moving. Sorry, can't be less than not moving. So there is no, the graph doesn't extend down here. But if you extend the line, that's your y-intercept. That's your work function. The slope is like this, and you have Planck's constant right there.
The slope?
What?
The slope?
Houston has
The
turtles.
slope is Planck's constant. Hey, but what if we have a different material?
They also have like the most
It's just a
What if we have a material with a larger work function?
Well, that's lower down.
Houston's full of that.
It goes like this. It starts down here,
Literally, it's full.
and it looks like this. It still has the same slope.
It's a constant.
It doesn't matter. It could be either one of those. Can the HC be this way?
Ah, now, which H do we use? Hey,
Depending on what.
it depends on what this is in. If this is in joules, then it'll be this one. If this is in EVs, then it will be this Planck's constant.
Don't use HC.
We don't use HC, not yet. We'll get to that. All right? So whichever one you get, whichever joules or EVs, use the appropriate one. hey, this is a really important spot right here. This spot right here helps you solve many, many, many problems. This is called
The x-intercept.
Threshold. Ooh.
So where's it at on the color? Is that like an orange? Like a dim orange?
It depends on the material, okay? It depends on the material. So,
That's a
girls. All right. Threshold frequency. The threshold frequency will help you figure out what the material is and what your work function is. Because at the threshold frequency, what's our kinetic energy? When you're right here, you're at 0. Okay, so they'll say something like this. Remember I said red didn't work? What if it was exactly for this particular substance, red doesn't work? Now, for another substance, red might work. It depends on what the work function is, right? So, let's say red didn't work, and let's say it was 650 nanometers. 650 nanometers, when you shine that color red at the material, nothing happens. No electrons break free. Now, if you're at 651, electrons start to pop off. If you're at 650 or below, nothing. Okay? So this is our threshold frequency. Ooh, is it our threshold frequency?
That's the wavelength.
This is our threshold wavelength. How do I turn threshold wavelength to threshold frequency?
Velocity.
All right. Velocity equals frequency times wavelength. Okay, what's our velocity though? Speed of light, c. Okay, so frequency equals c over wavelength, right? So this is 3E8 meters per second divided by 650. Uh-oh, I got to convert that to meters, e to the negative 9th meters. Okay, work it out. What's my threshold frequency?
4.6 e to the 14th.
Thank you, Ian.
4.6 e to the 14th hertz, or 1 over seconds, right? Okay, now, everybody, when I'm at the threshold frequency, what's my max kinetic energy going to be?
What?
When I'm at the threshold frequency, what's my max kinetic energy going to be?
0.
0. This is really important. At threshold. Trash can.
Must find trash can. All the way.
Pass that down. Oh, you're supposed to catch it. Don't dodge
Nice
it.
reflexes.
Throw it into the trash can for me.
It looks like he's about to go samurai. Not a problem here. Let's do trash cans.
Come on, dudes. Get it done.
Yeah.
So,
Same letters. Same syllables.
okay, everybody, this is 0 when this is threshold. So HF equals work function. So that's H times 4.6 e to the negative 14th hertz equals my work function. Okay, which H do I use?
First one.
Which one? Standard one?
Standard.
Standard units. Okay, so this becomes, what, 6.63 e to the negative 34 joules second.
Small amount.
Yes. So what's my work function?
Why do you put negative 14?
Oh. Sorry, positive. Sorry. So what's my work function? Ready.
Alright, 3.05 e to the negative 19.
E to the 19th what?
We're going to go with, what is it, work or something? Watts.
It's joule.
I'm just kidding.
Okay, what's the hertz?
Joule per
That's
second squared. I mean joule.
second power. Yeah, because that's what you need. It's a joule unit.
It's energy, right?
Yeah.
No, it's, well, when they say work function, remember the units for work is still joules, right? So it's the amount of work required to break it free in joules.
It's like 4.6 e to the 14.
Okay, really small. All right, now, those units are really cruddy. I don't like that. Convert that to EVs for me, please.
1.906.
Thank you.
1.9
Why did you
E.
say it?
I was waiting for the okay. I was waiting for the okay to go. You guys just shouted
No,
out.
no,
What
no.
if some slower people
Let me use
wanted to
that.
calculate it?
1.906.
1.6 e to the negative 19th.
9.
What are you talking about?
Yeah, what are you doing?
Look on your constant sheet.
Yeah, that's a charge of an electron.
We're
Yeah.
doing the answer.
The equation.
We already figured the
We're
answer out.
telling you the answer.
Yeah.
Oh, you tell me the answer. Oh, that's no good. It's right there.
Yeah, it's 1.6.
1.6 e to the negative 19 joules equals 1 EV, right? So you can convert it. So what's your answer?
1.9.
1.
1.9.
1.91 what?
EV.
EVs. All right. That was a lot of work. Let's make it easier.
Okay.
All right, everybody. Watch this. We're going to make life much simpler. What's H? What's frequency again?
What do you mean?
Speed of light over wavelength, right?
Yes.
If I sub that in, look what I get. K max equals HC over wavelength minus work function, right? We got that?
Yes.
Now look, here's where HC comes in. Here's where HC comes in. What's that? Look what I've got. This is my threshold wavelength. What units is it in? Nanometers. K max equals HC over lambda plus work function. But when I'm at the threshold wavelength, that's 0, right? Oops, dadgummit. That's minus. Sorry, I'm making all kinds of plus minus mistakes today.
Bad.
So I get HC over threshold equals work function. But this number for me is in nanometers. So my equation becomes 650 nanometers equals work function. Which HC do I use?
The
The
nanometer.
nanometer one. Whoa, look, 1240 nanometer. Oh, EV nanometers, sorry. EV nanometers. Nanometers cancel, and hey, look what I get. 1.91 EVs. Whoa, that was fast and easy, right? Now, do you see the benefit of using EVs? If you don't use EVs and you use joules, you get a ridiculous number. When you use EVs, it becomes a simpler number to write down, right? They are mathematically the same, right? Okay, so remember this quick little trick right here. Don't go ahead and calculate the frequency unless they ask for it. Just put the substitution in and solve it. It's a lot faster, okay? All right. Everybody get out your review packet. All right.
Are we done?
Done?
No.
No, we're not done. We got another thing to go yet. Let's see, which one will we use? Oh, I know what I was going to say. Get out your review packet, and then I want you to go to, let's see, which page? Oh, here. There you go. Okay, on your review packet, I want you to turn to free response problem 500. It looks like this. Looks like this. Right down here. There's two problems on that page. Okay? Problem 500. All right, everybody, work problem 500, go. Okay, I know several of you are kind of stuck on a couple of things. Can I hit the lights in the front of the room? Colin, can you get that for me back there? Okay. Go ahead and hit. There we go. All right, so right here. Here's our battery. Right now our battery is 0 volts. There's 0 current. And here's my light. It's on purple or violet. And here's my photosensitive material. Okay, notice no light, no electrons. I start to shine light on it and hey, there they go. There's my electrons popping off and going to the right. Notice I have current, right? Okay, when I shine brighter light, what should happen? More electrons, right? But should they be faster?
No.
No, they should still have the same maximum energy. So when I shine brighter light, I get more. Notice some of them are going fast and some of them are going slow, but the maximum energy is staying the same. All right, now, notice I get more current. So when I back it down, I get less current. Crank it up, I get more current. Okay, now watch. My volts. What do I want to make this side? To stop them.
Whatever it's equal.
Negative.
I want to make it negative, right? And this side positive, okay? Oh, I made it the wrong way. This side's negative, so it attracts them, right? Okay, so I want to go the other way. I'm going to go this way. And notice what's happening. Ooh, I'm to 0 current.
Back it up.
That was kind of cool.
I'm going to back it up.
Oh,
Oh,
we got a current.
Give me 50 feet.
Wait, make it almost hit it and then stop it.
It looks really fun to play with. It's like dodgeball.
okay, notice right here that most of them are turning around, but there are still a few that make it, right? I still have a little current.
Oh, look, those barely stopped. Look at those. I was barely stopping. Ow, you almost got there. Too bad.
Relax, it's okay. All right, now when I go this way,
I think that's more than they can make it.
okay, right there, 0. So no more current. They go up and they don't quite make it. Okay, look how many volts. 0.48 volts. Okay, tell me, what's the energy of this one that just went up here and stopped?
Ah.
0.8.
0.8 what?
Electron volt.
Electron volts. Because look, over here they have kinetic. Over here they have potential, which is V times Q. The V is 0.8. What's the Q? An electron. So I have 0.8 EVs. So when they tell you in this problem it takes how many volts to stop them? 4.5 volts to stop them? How much energy did they have? 4.5 what? EVs. Very good. Awesome. Awesome, awesome, awesome. Thank you, that's fabulous. Did you just do that?
Oh, I could do that.
All right, does that help you out? Okay, and just so that you know, watch this. Let's go back to 0 volts here. All right, when I go back to 0 volts.
You almost crossed the river.
Uh-oh, what happened?
Look, those are going backwards. They're going to shoot for.
You ruined it.
All right, 0 volts. We can also find the threshold frequency by doing this. We just keep going down this way until my current goes to...
We are on I-35.
right there. So 532. Oh, it looks like some of them are making it in the diagram.
Wait, no, they're coming. They're coming. Put them right there. Oh, what the heck? They broke it.
Jam up. It's .000.
Oh, what?
What's wrong with it?
I think it's because you have no volt.
No. All right, 541, nothing. 535. Oh, looks like around 535, 538, somewhere in there they start to pop off, right? Okay, so the threshold frequency of this one is somewhere around 535-ish. Okay? When they start to pop off, right? Okay. Can you solve the problem now?
It's like a horse race.
I was just doing
I gotta turn that off. You're all gonna stare at it.
That's it, mess up.
All right. The sodium photoelectric surface has a work function of. So they gave you the work function in this problem.
Is it normally the find?
A lot of times you'll have to find it. Okay? And they'll give you, in some of these other ones, you're finding what the work function is. Okay? Like the one right above it. We'll work that one in a second. Okay, the work function is 2.3 EVs. It's illuminated by an electromagnetic radiation and emits electrons. The electrons travel towards a negatively charged cathode and complete the circuit shown. Okay? Potential difference supplied by the power supply is increased. When it reaches 4.5 volts, no electrons reach the cathode. So when this gets to 4.5 volts, the electrons stop and turn around. Okay? So when they stop, how much energy do they have? They start with kinetic, they go over here and stop, so they have only electric potential, which is VQ, which is 4.5 EVs. That's how much energy they have. For the electrons emitted, what's the maximum kinetic energy? Well, we just did part I. Or part, 1I. It's 4.5 EVs. Okay, double I.
Really?
The speed of the maximum kinetic energy. Speed at this maximum kinetic energy. All right, well, this is energy. I just got to turn it into 1/2 mv squared. Right?
Yeah.
Let him ask a question.
Isn't it asks for maximum kinetic energy? Isn't that equal to 4.5 minus the 2.3? No. Okay, so okay, yeah.
Because in order for, if this voltage is required to stop it, that means they must have had this energy at the beginning. So that's its maximum kinetic energy. Because the kinetic energy they start with equals the potential energy that they end with when they stop. And that's VQ, and so that's 4.5 volts times 1E, or 4.5 EVs. All right? Now, our 4.5 EVs is 1/2 mv squared. A couple of changes we probably need to make. Change number one is, you got to convert that to joules. So you got to multiply that by 1.6 e to the negative 19 joules per coulomb and do your conversion. I'm sorry, joules per EV, sorry. And convert that. And then, what mass? Mass of an electron. And just look it up. Turns out to be what? 9.11 e to the negative 31st, right? So 9.11 e to the negative 31st kilograms. And then after much work, you get the velocity. Who has that? What is it?
1.3.
1.3 E6.
Meters per second.
6 meters per second. Okay, when would you know you made a mistake here? What would be a dead giveaway?
It was faster than speed.
Yeah, if you get something faster than the speed of light, you know you messed something up, right? Okay, so if you get anything past 3E8, you might want to check it. Probably did something, messed some calculation up, okay? All right, part B, calculate the wavelength of the radiation that was incident upon the sodium surface. Okay, we want to know wavelength. But in order to know wavelength, velocity equals frequency times wavelength. I need to know the frequency of the light, right? So what can I use?
K equals HF minus work function.
HF minus work function. Excellent, because they gave the work function and we know what the max kinetic energy is because we just calculated it, right? Now, I don't want to know frequency, so how can I modify this? There you go. Make it nice and easy for us. That's HC over F, right? Because remember... Oh, crap, thanks. HC over lambda, thank you, minus the work function. Now, this was 4.5 EVs. We calculated that in the first part. HC over lambda, we know the work function. Do we know the work function? Oh yeah, it was given. 2.3 EVs. And so all we have to do is plug in the appropriate HC, which would be,
140.
yeah, this one.
1240, yeah.
All right? So this becomes 1240 EV nanometers. Okay, EVs are all going to cancel. I'm left with nanometers. I don't remember. What did we get here? 182 nanometers. Hey, can you see that?
No.
What range do we see? 400 to 700 nanometers. So what is this? See, its wavelength is smaller than 400. So that means Roy G. Biv, this is the 700 nanometer side, this is the 400 nanometer side. So it's out here in ultraviolet. So that's an ultraviolet light of some kind, right? Now, yeah, they're probably not going to give you gamma rays or X-rays on this one. So it's not that much farther than violet. So we're going to assume that's ultraviolet. Besides, remember, light is a very narrow, tiny part of the spectrum. So even if we go a sizable amount away, we're going to still be in ultraviolet. Okay, calculate the minimum frequency of light that will cause photo emission from the sodium surface. What are they asking for? They're asking for the threshold frequency. And the key in the threshold frequency is? Yeah, Kmax equals 0. Okay, that's 0. And they're asking for frequency. So H threshold equals the work function. Our work function was 2.3 EVs. I'm looking for frequency. Okay, which H?
4.14.
Okay, I used the one with EVs in it, right? Because I'm working with EVs. I use 4.14. 4.14 negative 50, oh, e to the negative 15 EV seconds. All right, that'll give me my threshold. Threshold turns out to be 5.6 e to the 14 hertz. All right.
Oh, because this is
Okay. Okay. Let's make sure you get these right.
Oh, assuming that's the limit, I get lead 0.
We can do some of it. We can do through photoelectric effect. We're going to work our way through this. A lot of these are new, which is why we're going to need to work them out. So here's what I want you to do. Because we're running out of time and because I'm mad at you. I want you to work the one on the top of the page. And I want you to work on the one on the bottom of the page before. So 380 and 683. Okay? Yeah, same page. The multiple choice ones on there are nuclear reactions. You could probably do the nuclear reaction ones because you probably talked about that in chemistry already. But I'm not requiring you to do that, okay? So you're doing the one on the top of that page, which is 683, the one right above, and then go to the other side of that page at the bottom. I want the graph, page problem 380. Okay, work both those out.